Thank you, Randy. And I really appreciate this opportunity to speak to everyone. This is actually material research that I did a few years ago, presented at the AMS, I think in 2017. And so I thought this was a great opportunity to kind of review for people some of the research I've done and others have done on organization of occlusions in mid-latitude cyclones, given the impact that can have in terms of blizzards and heavy snow across the region. So what I'm going to start with is just a snowfall map. This is a snowfall map from a storm about 4 years ago. A basic question here. Do you think this snowfall pattern is predictable? Not necessarily the exact location of the bands, but do you think forecasting a double band of snow and both bands occurred within the same 24-hour period, it is predictable? And then as you think about that, think about how would you message that? How would you talk to people about that both during, and then how would you anticipate it as it was occurring? And I'll try and answer some of those questions at the end of this talk. So we have here two bands of snow, a northern band that's just north of Sioux Falls, and a southern band that goes across northwestern Iowa into southeastern Minnesota, and then the two kind of appear to merge over with central Wisconsin. So how does this happen? How do you get these two bands to actually form like this? And as I said, can this be anticipated? And I would argue that this can be anticipated. Otherwise, I guess I wouldn't be doing the talk. But it's all part of the occlusion process, or the cyclone evolution from least cyclogenesis all the way through the occluding process of the storm. And if you understand how that process occurs, you can kind of anticipate that happening by looking at model forecasts and also observing satellite and radar data. So what I'm going to do is just provide a brief review of TROWALS on work that's been done in the past and some conceptual models of snowfall within the TROWALS. Then I'm going to examine two cases. These are from a while ago. One was from November of 2005, so 15 years ago. The other one is the famous Dome Buster storm that took down the Metrodome roof in December of 2010 that Minneapolis actually just tweeted about a couple days ago. So we're going to examine the evolution in both storms of the dynamic tropopause and of the jet streaks, and look at the differences in the synoptiscale with these two storms initially. And then we'll go down into the mesoscale and look at frontogenesis and stability and vertical motion within the forming occlusion. So we're going to start actually before the storm starts occluding and go through the occlusion process. For all of this, I'm going to use a 0-hour analysis from the rock. So that basically they have the same basic physics with it. And the same analysis scheme and the same grid spacing, which is 20 kilometers in this case. You'll see a little bit of radar imagery initially with these storms that I got from NCAR. So this is from a comment module from a few years ago, but this is the classic view of what a TROWAL is. So for those of you who took synoptic meteorology, maybe have to draw back a few years, this is the classic conveyor belt model that Toby Carlson came up with in the 1980s. And you start with the warm conveyor belt. And the traditional view of the warm conveyor belt is it starts well south in the warm sector, and then it traverses northward, maybe rising a little bit, very slowly in the warm sector. And then it hits the warm front, and it rises more rapidly as it crosses over the warm front and gets into the cooler air. And the traditional thought is that the warm conveyor belt would then turn anticyclonically to the northeast and then turn east. And then you can see this in the storm by looking at where the radar, the stratus and precipitation was, where the major vertical motion was, and then as a warm conveyor belt got higher up, you get altostratus, maybe some light snow or virga, and then you get the streaming cirrostratus at the edge of the storm. Well, what others have found, such as Jim Moore back in the early 2000s, is that if you have a slow-moving upper-level system, you can actually split the warm conveyor belt. The warm conveyor belt will still have that anticyclonically churning portion of it, but closer to the upper low, the warm conveyor belt will actually be turned cyclonically around the low and into the northwestern part of the storm. Initially, when Carlson came up with his conceptual model, he claimed that he had argued that most of this area was due to the cold conveyor belt, but subsequent work by Dave Schultz and Jim Moore showed that it was actually there was a cold conveyor belt, but the precipitation moisture actually came from the warm conveyor belt being wrapped cyclonically around the low. The other thing that he talked about was the dry conveyor belt, which comes in behind the storm and then also has two branches. And what we're going to look at here is the branch that comes around the storm and begins to turn northeastward. And he really never talked a lot about that in his papers, but this actually ends up being a really important portion of how the TROWAL actually evolves in time, because it's actually a signifier of the upper level jet rounding the base of the trough and coming northward. And it's what cuts off, eventually separates the TROWAL precipitation from the main precipitation with the cold front and warm front farther east. So I'm old school, so you get to see GEMPACK graphics, which there probably not many people do anymore. But I can't find a better example of a TROWAL in a cross section than this, so that's why I use this. But this is theta E in a cross section in red. Potential vorticity is shaded. And then what the TROWAL looks like in a cross section, if you just take any cross section through a theta E ridge at 700, say, with a significant cyclone, is it looks like a trough or a canyon of warm, moist air surrounded by colder, drier air to each side. So you see here the 310 theta E line goes down to about 600 millibars within the TROWAL, but it's up towards 400 millibars on either side of the TROWAL. So you have this relatively warm, moist air in the middle, surrounded by cold air. And that causes two things. One, obviously you have moisture, which is critical to getting snow, but also look at the slope of the theta E lines on either side of the TROWAL. What does that tell you? Well, there's two things that it should signify. One is you've got a front on both sides of the TROWAL. You've got a cold front, which appears to be more of a mid-level or upper-level front on the southeast side of the TROWAL. This is towards Davenport, Iowa. And you have a warm front, which you can actually go back to see a reflection at the surface that actually extends up on the north side of the TROWAL. And in this case towards Spokane, based on how I drew this cross section. And also, so you have a boundary there that can provide lift. The other thing you note is by having a slope, the more vertical the theta E lines are, the more unstable it is, or less stable it is. It's probably a better way to say it. It's not unstable, but it's less stable. And so I've also got less stability within the TROWAL here, but also on either side of the TROWAL, because I have more vertical theta E lines. Theta E is decreasing much less on the edges of the TROWAL than it is, say, in the colder air over on either side. So I've got moisture, I've got instability, and I've got lift. So those are the ingredients we need to get heavy snow and banded snowfall if you have frontogenesis in place. So that's why the TROWAL can be a very, very good producer of heavy snow across in an area. Now, if you look at a TROWAL on a map, you can, as I said, you can look at like 700 theta E and stuff, but if you really want to see how it evolves, what you really want to look at is pressure on a theta E surface, and you can do this in AWIPS. And so this is pressure, I think, on a 310 surface, or 315, or 305. And you can see here, if I follow the warm conveyor belt, you see it go to 800, 700, and 600. So you see slow rising in the middle of the TROWAL as the air traverses through it around here. And this is a very well-developed cyclone. It produced almost 2 feet of snow in portions of eastern South Dakota into north central Nebraska. So this is an extreme example. The other thing you can see is you can see pressure gradients on either side. And again, if we go back to our cross section, this would be like your cold frontal side of the TROWAL. You have cold air to the south, which is a little bit different than what we normally think of. And you have a tighter pressure gradient. So the cold front is more sloped than the warm front, which is on the northwest side of our TROWAL. You can see that there's a gradient there. The gradient is generally weaker, except up here near Lake Superior. And so in general, you have more instability or potentially less stable air on the cold side of the TROWAL than you do on the warm side of the TROWAL. But you can see the evidence of both fronts there by looking at the pressure gradient on either side of the TROWAL. So by looking at this, there came up 2 conceptual models of how precipitation occurs with the TROWAL. Back in 2005, Jim Moore and colleagues at St. Louis University, they said, well, if you have the warm conveyor belt, which is right here, it comes back around, you're going to have frontogenesis to the north, on the northern edge of that warm conveyor belt with our warm front in essence. And south of that mid-level frontogenesis, you're going to get banded snowfall. And also south of that mid-level frontogenesis is an area where there's going to be less stable air to help reduce the scale of that band and produce very heavy snow potentially within the trowel. And you can kind of see that in that cross section here where you have this instability, initially convectively unstable, then symmetrically unstable, approaching this area with rising frontal, with a frontal circulation. Michelle Hahn and colleagues at the University of Illinois 2 years later got a different scenario. What they said is, well, what we're seeing is that there's frontogenesis along the cold frontal side of the trowel. And you can see here's the theta E ridge here. And so all our lift and all our snow is actually south of the theta E ridge. So it seemed like there were two conflicting views on how you got snow within a trowel and where it would be located, which for us as forecasters can be a big deal, because if you see the theta E axis or ridge, which side of the ridge do you put the heavy snow on? And so to me, that was something that worth investigating. What we're going to see here is that they're both right. It depends when and how you look at the trowel and how the trowel forms or the occlusion forms. So we're going to start looking at the two storms here, December and November. I'm going to do the upper levels together so you can kind of see the differences, because there's some pretty big differences in the synoptic scale, and that drives everything else that happens within the storm. And I know this is a little bit busy. I apologize, but I wanted to get the big things on here. And the two biggest ones is I wanted you to see the jet streak at 300 millibars, which is shaded right here. These contours are in meters per second because I did this at the AMS and they don't like non-metric. So, but think of this as a 150 to 160 knot jet coming down the backside of this trough. And notice that the flow is relatively northwesterly flow across the conus at this point in time. So it's not very amplified as this jet's moving in. And we can see our PV anomaly to the north of our jet streak, which is pretty typical. And you get all the pressure advection here in the left exit region of the jet. If we go to our November case, we see a much more amplified flow. And we see that our jet is beginning to round the base of the trough. And so the trough is beginning to become negatively tilted as the energy, the jet energy, transfers from the upstream side to the downstream side of the trough. And so that does make a difference, as we're going to see in a little bit. So we have much more amplified flow. We also are much more diffluent out ahead of on the downstream side of the trough compared to where we are here. There's diffluence over Colorado. But the difference in amplification and where the jet is located is going to make a difference in how these storms evolve. So as we move ahead to 0Z, you see the jet continues to dive downward. Our PV anomaly moves into Wyoming. We see all the pressure advection forcing for synoptic lift would be out ahead of it to the southeast of it. And we see that our jet continues to round the base of the trough here in our November case. And we see a really nice exit region here. And you have both the left exit region of the jet, and we have curvature working to produce a lot of divergence across Nebraska, Iowa, Missouri, Kansas at this time. As we continue to move ahead in time to 6Z, we see this wave continue to dig southward. We see the PV anomalies moved into Nebraska at this point. We also are beginning to see an amplification of the flow, more amplification of the wave here. And we're beginning to see also a jet streak beginning to form to the northeast, which is also going to be a little bit important to what's going to happen here. Meanwhile, in our November case, we see the jet streak and the PV anomaly have rounded the base of the trough, very negatively tilted at this point. A lot of diffluence across Nebraska, South Dakota, Iowa, and you can imagine there's just a ton of lift going on over southern Iowa with this jet streak at this point. And then if we go to 12Z, our jet continues to dig southward. We continue to amplify the storm. Our waves now really slowed down. Our PV anomaly, it had moved from western Montana into Nebraska in 12 hours, but in the next 6 hours, it moved from central Nebraska basically into eastern Nebraska. So it's really slowed down. As this amplification occurs, it slows the whole process down. And as this ridge builds out up ahead of it downstream, we begin to see this jet streak begin to build backwards just north of the international border. So we get this very short wavelength trough ridge developing over the eastern plains or western Great Lakes. Meanwhile, with our November case, you can see the upper low is well developed as it moves into the Omaha area. The jet streak continues to move northward towards northern Iowa. You've got strong PV advection to the south. So you just basically your classic cyclone going on here. You don't have, though, a northern stream jet really in place anymore with this storm. And finally, 6 hours later, we see the jet continues to dig southward. It's now over 160 knots. Our upper low has moved barely. It's moved into northwestern Iowa, so it's moving very slowly. Now most of the pressure advection, the forcing for synoptic lift, is now up north of our PV anomaly instead of southeast of it that it was before. There is still some to the southeast. We see a very tight gradient and southerly flow here. And we see our jet streak has increased to over 100 knots or 50 meters per second north of Lake Superior. So we've got a nice kind of short wavelength trough and the help with the entrance region of the jet to produce a lot of lift right in South Dakota and Minnesota and Wisconsin. Meanwhile, with our other system, it continues to wrap up. We see the jet streak move into the Mississippi River Valley, northern Mississippi River Valley, and again, strong diffluence across the Minnesota into Wisconsin and Michigan. So just as a brief summary in the synoptic scale, both systems are deepening mid-level waves moving across the central United States. However, the December 10th is an event of a jet digging on the backside of the trough. And so we have this amplifying flow. So it's very much amplifying the wavelengths. You go from primarily westerly or northwesterly flow to a very short wavelength trough ridge across the northern US. The 25th November case, the jet is already downstream of the trough axis. So you're basically taking that trough and making it negatively tilted and forming what we would call a classic occlusion at that point. So we're going to now focus in a little bit on the mesoscale with this storm. We're going to start looking at the TROWAL itself as it forms. And so in the lower corner here is the radar depiction at the time of this cross section, and the yellow line is the approximate location of the cross section within it. And so on this cross section, you have frontogenesis in yellow. You've got EPV shaded, anything less than 0.25, so either weakly stable, and once you get to the greens, it's below 0, so it's symmetrically or convectively unstable on there. And then the blue is RH, and anything less than 80 is dashed, and 95 is solid. So you've got saturated air within and above our warm front here. This is our warm front sitting right here. You've got a lot of instability in this very dry air, which is probably associated with the dry conveyor belt that's moving northward with our jet streak. But you can see that instability actually comes into the saturated area, and you have about 100 to 150 millibar deep layer of relatively unstable air that either symmetrically or convectively unstable. And most likely there is shallow convective instability. At least that's what has been found by people at the University of Illinois. And so you've got the ability here with strong lift, saturation, and instability to produce a narrow band of relatively heavy snow. And you can see that there's pretty heavy precipitation falling across southeastern South Dakota into north central Nebraska at this point. In fact, they were getting heavy snow and freezing rain at this point. When we look at the vertical motion, you can see that it shows up in the vertical motion as well. You've got this area of very strong lift from 800 all the way up to 600 millibars associated with our warm front as well. There is lift back to farther to the southeast, and if you look, you can start seeing the signs of maybe some precipitation beginning to form along the Kansas and Nebraska border. And that's probably associated with our cold front beginning to come northward. So as we continue to move ahead in time, notice that we still have some instability along our warm front. It's beginning to constrict a little bit. It's becoming a little bit more stable with time, but you still have a lot of saturation there, at least weak stability, if not some instability there as well. But you're also beginning to see some saturation back farther west right in here, and you're seeing convection forming in southwestern Iowa. And that's a sign of our cold front. And we'll look at that a little bit later. It's a little bit harder to see in the cross section here. So when we look at this, we see that we're beginning to get some lift here on on the very south side of our cross section with the cold front, and we still have our fairly strong lift, although not quite as strong as what we saw earlier along our warm front moving northward. So we still have this band of snow and rain, or freezing rain, across South Dakota and Nebraska, but it's not quite as vigorous as what we saw even 3 hours ago. As we continue to move ahead in time, we see this area of low-level instability. We see saturation continue to increase on the south side of our cross section. Again, that's associated with our convection, which has become more widespread on the south side across northern Iowa. And we also see, again, this warm frontogenesis here, and we see some instability yet, but it's becoming, again, more shallow and it's beginning to move a little bit farther away from our front. So we continue to see increasing lift on the south side of our trowel, and we see lift weakening on the north side of our trowel. And you can see the echoes, there's still decent snow falling, but it's becoming a little bit more weaker, not as heavy as it was earlier, especially when you compare it to the new band forming across northern Iowa. At 12Z, now we see that most of the instability, again, a lot of this is in the dry air, but right in here is actually more along our warm front, or our cold front, sorry. It's become much more stable along our warm front. And you can see that in the radar picture, the echoes, the precipitation rates are much higher now on the south side of our trowel than they are on the north side of our trowel. And this also shows up within the vertical motion, much weaker vertical motion now along the warm front, above the warm front, than there is above the mid-level cold front that's moving in. And when we move to 15Z, we continue to see the increased stability above the warm front. Frontogenesis is still, it's much more messy along our cold front. And you kind of see how it moves here. You can see the better in the theta E lines. Not particularly unstable, but the one thing that the cold front has going for it, even if it's not very unstable there, is you have the exit region of the jet, and the jet streak punching northward. And so you're able to utilize a lot of dynamic lift that gets the cold front and the warm front, or the cold frontal circulation and the upper jet circulation working in tandem to produce a much stronger lift across the area. And we see that here where there's very little lift remaining, at least in the rock through this cross section. There's obviously a little bit of snow up there along our warm front, but there's a tremendous amount of lift along our cold front. So we see how the lift has shifted from the north side of the trowel to the south side of the trowel as that jet streak has moved northward over time. So we can look at this in a plan view as well. And so in the upper left is frontogenesis at 850 in white with 800 to 700 EPV, same color shading, except I have two sets of blues for weak stability. Same thing at 700 millibars with 650 to 550 EPV. Lower left is tropopause pressure, which is shaded and mean sea level pressure. And then on the right is the 600 millibar theta E and 600 millibar vertical motion. And so we start back again at 3Z on the 28th, and you can see very strong frontogenesis. The warm front really shows up well here. You really can't see much in terms of a cold front at all, in terms of frontogenesis at least. And notice how all the instability is backed up right up to the edge of where our warm front is. So you can imagine this unstable air is being advected towards our warm front, gets ingested, it's saturated, and you can really produce a strong circulation. And you see that in the vertical motion right here. Strong vertical motion across our entire warm front from Nebraska into southeastern South Dakota. Meanwhile, you have the theta E gradient forming across Kansas and Nebraska with lift along it, both along the surface. This is pretty close to the surface cold front down here in Arkansas, but along the mid-level front where our jet streak is punching northward or our PV anomaly is moving northward. And so we'll follow that as this goes on. And as we move to 6Z, we see our anomaly continues to move north. We see strong lift forming in southwestern Iowa. Again, not really a lot of frontogenesis there. It's more that there's just a lot of instability, and there's probably an upper front higher up in the atmosphere that we're not capturing with this, as is indicated by the theta E gradient we're seeing at 600 millibars. Notice how much more stable it's become near our warm front, as the warm front also is a little less frontogenetic. It's more weakly stable at this point instead of unstable to the east of our warm front. So we're seeing that instability gradually wear out. And remember, we didn't have a northern stream jet to really work with this warm front. So this frontal circulation is really being driven by strong frontogenesis combined with a pretty unstable environment. And as that instability begins to weaken, we start seeing that the lift also begins to weaken. It doesn't shut off right away, but it begins to slow down a little bit. The snowfall rates may be starting to taper off a little bit. Maybe instead of the 1 to 1.5 inches an hour, you're getting 3/4 to 1 inch per hour. Still a lot of snow, but not quite what we were seeing 3 hours ago. As we continue to move ahead in time, you can see the nice theta E boundary at 600 millibars here, this humidity front, which is what Mass and Schultz called it back in 1993. Strong lift across Iowa where we're getting convection. Again, really not a lot of reflection in terms of classic frontogenesis in this case. Much easier to see this cold front when you look at theta E in the mid levels. We continue to see the warm front, the frontogenesis along the warm front. It continues to be fairly weakly stable, but much more instability is back to the southwest. It's back towards the south side of our forming TROWAL here, which you can see in the theta E gradient. And again, that lift is right ahead of our PV anomaly in here, which is all the way down to almost 500 millibars near Omaha. Moving ahead to 12Z, we continue to see that the warm front shows up well at 850. It continues to stabilize to the east of the warm front. And instead we see kind of some disorganized frontogenesis along our forming cold front. But I think, again, you can see how all the lift continues to be out ahead on the south side of the TROWAL along our cold front, where we saw that really nice band of snow and maybe some rain if it was warm enough across northern Iowa moving into southern Minnesota. And our lift is much, much weaker along our warm front. And we see the same thing at 15Z. You continue with pretty weak lift on the north side of the TROWAL, where our warm front was. It's become increasingly stable in that area, and it continues to be relatively less stable, but strong with the stronger dynamical forcing from the PV anomaly and jet streak moving northward. So let's review that. Early in the event, there was strong lift and heavy precipitation along the warm front where weak stability or even instability existed. But as the event progressed and the atmosphere above the warm front began to stabilize, we see the ascent and the precipitation rates slowly decrease. It doesn't end in this case, but they slowly decrease. And we see that the convective instability that was present in the exit region of the jet just ahead of our dry slot, you want to think of it that way, and ahead of the upper level front, produced convection and heavy precipitation along the boundary. And this became the dominant band of precipitation after 12Z. That's where the heavy snow or heavy freezing rain, if there was, I think it was mostly snow at this point, occurred across Minnesota and South Dakota at this time, as that band became the dominant one for the remainder of the storm. So now let's look at our December case, the dome buster case from Minneapolis. We're not going to actually focus on Minneapolis because that was all warm frontal precipitation. So sorry for those in the Twin Cities. We're going to focus farther west into the eastern Dakotas and northeastern Nebraska, where the TROWAL actually did set up. And so we start here at 6Z on the 11th, same cross section as before. You can see the really nice warm frontal precipitation moving into the Minneapolis area at this time. It initially was freezing rain. I think at this point it changed over to snow in Minneapolis. It had been freezing rain farther south. But you can see a pretty disorganized area of precipitation across Nebraska, South Dakota border. This area of more organized precipitations along near the surface front that has, with our cyclone that's moved into eastern Nebraska at this point. But you can see nice frontogenesis that extends northward along our cross section. But notice in this case, at least, and again, this is one case, not all cases, it's really not that unstable here. Maybe some weak stability, but you don't see the unstable air that we saw with the other case. In part, this is because, as we'll see in a little bit, the warm moist air hasn't actually wrapped back into the system yet. But there is, if you recall, we have our wave that's moved down southward into Nebraska with our jet streaks. So you do have some dynamic forcing for lift, which is why we're seeing this area of precipitation north central Nebraska at this time. And when we look at vertical motion, you can see you do have ascent in that same area, just above this area of frontogenesis between 800 and 700 millibars. We move ahead to 9Z. Again, things are, maybe this precipitation is becoming a little bit more organized across here. Again, you see kind of the warm frontal precipitation in eastern Minnesota into Wisconsin, the cold frontal stuff from Kansas into west central Iowa. Again, very stable, relatively stable above our front, but with that strong dynamics, with that digging wave, the short wavelength that's developing across the area, we still end up with very strong lift continuing to develop to the west and northwest, or I should say northwest of our surface cyclone over eastern South Dakota. And you can see that here. As we move ahead to 12Z, as we shift with the low, notice our front is becoming better organized. It's not more unstable, but we're actually getting better frontogenesis across the area. And we're beginning to see a band of snow that extends from west, south, La Crosse area along I-90 all the way back into southeastern South Dakota. So, and if you recall again, that both looking at the slope of these theta E lines and the slope of this frontogenesis, that this is actually a warm front. So this is an extension of the warm frontal precipitation is beginning to extend back westward to the northwest of the low. And we have this area of convection, or showers at least, along the cold front. And notice near where our triple point would be, there's actually very little precipitation. And that's not an artifact of having no radar nearby, as we'll see in a little bit. And that's part of the evolution of this system. So when we look at the vertical motion again, we see this area of strong ascent on the warm side of our front and what will eventually be the north side of our trough. So essentially you're seeing a warm frontal extension to the northwest, which becomes the opposite of what we saw in the other case. We move ahead to 15Z. Again, you see the really nice warm frontal band extending from western Wisconsin through the Minneapolis area and back towards Sioux Falls. Very strong frontogenesis through this area. Again, not very unstable, but if you recall our upper wave, and you can almost see it in the radar picture, sitting somewhere between Omaha and Sioux City. And so you have this just very strong dynamic forcing interacting with this front, this upper PD anomaly interacting with this front. And so you're just ending up with this intense lift on the western side of the trough, of the western side of the system, or within the TROWAL, on the north side of the TROWAL in this case. So much like what Jim Moore was showing earlier. And at 18Z, again, you see nice convection to the south, mainly south of I-80. Nice warm frontal band from Wisconsin through Minneapolis back towards the northwestern Iowa. And we see that lift continuing in that area. So I hope this convinces you that this band, in this case, the precip northwest of the low, is associated with the warm front in this case. In the other case, we saw it initially was with the warm front, but actually moved to the cold front over time. Well, in this case, the warm frontal precipitation actually becomes more intense over time. So at 6Z on the 12th, we look at the same 4-panel that we had before. You see some instability here. You see the frontogenesis, it's kind of disorganized across this area. You can see the kind of disorganized lift, with the upper wave here along the Nebraska-South Dakota border. You see it just north of the northwest of the wave, or northeast of the wave, I'm sorry. The cold front and the warm front moving through Minneapolis. As we move ahead in time, you see the warm frontal band frontogenesis across Wisconsin into Minnesota at this time. And at the theta E, you begin to see a theta E ridge starting to form across Iowa back into northeastern Nebraska. Not the pronounced, wrapped up system we saw before, but that's because our jet streak, if you remember, is still diving southward towards Missouri and eastern Kansas. And so you end up with the dry slot is actually moving southward. So you can't kind of cut off that that plume of moisture in the trial that you'd see in the previous system. But you still see this lift continue to organize across this area. You see the warm front here, but there's still a lot of disorganization with this system at 9Z. We move ahead to 12Z. You see that the upper waves now moved into eastern Nebraska. The frontogenesis continues to strengthen along the warm front. And you can see some frontogenesis beginning to form here across southeastern South Dakota. You see that at 700 as well. But also notice that remember I mentioned about the lack of radar imagery. You don't see the frontogenesis nor really the lift really connect here between the warm front up here, from Wisconsin back into South Dakota, and the cold front more in Iowa down through Kansas. And so, and we'll see that in the next slide even better, where you see the warm frontogenesis back through here, even shows up better at 700 millibars from Sioux Falls area back through northern Wisconsin, or 850 northwestern Iowa through Wisconsin. And then the cold frontogenesis at 700 is from the Des Moines area southward, and kind of very little frontogenesis in between. There's almost a fracture at the triple point, which is kind of like the paper back in the 90s by Shapiro and Kaiser kind of talked about this with some oceanic cyclones. That appears to be what's happening here. And you can see how there's a weakness in the gradient between the cold front and the warm front to the north as well. As you have our theta E ridge edging back to the south, you're getting intensified lift again across southwestern Minnesota and into western Wisconsin. And finally, at 18Z, so TROWAL matures. You see the nice theta E ridge back across Iowa now. You see the warm frontal lift, very strong lift all the way from Minneapolis area, northwestern Wisconsin, back into northwestern Iowa. You see the frontogenesis at both 850 and 700 in the same area, and then that kind of that gap, and then the cold frontogenesis here. So this really shows how this front, this band of snow, is really warm frontal in nature and is north of where our ridge is. And that's the key point. So with these systems where the jet is still diving into the base of the trough, where the trough is amplifying, you're going to focus most of the time, not every time, you're going to focus your lift on the north side of the theta E gradient. And if there's a trough forms, it's going to extend northwestward along the warm front. Whereas with the systems where the jet is coming around the base of the trough, we're going to see the band of heavy precip move from the north side of the trough to the south side of the trough over time. And that's kind of what I summarized here. So the key is knowing where your jet is. If you know where the jet is within the deepening cyclone, you can predict how, you should be able to predict or develop a conceptual model for how precipitation should evolve. If it's downstream of the trough axis, you're going to see a band initially along the warm front. You still have the warm conveyor belt going over it, so it's going to be still got frontogenesis and instability to work with. But as time goes on, as the system begins to occlude, as the dry slot forms, and as that jet streak moves northeastward, you're going to see precipitation form along the cold front, and that is going to eventually become the dominant precipitation. How long it takes to become dominant depends on a lot of other things. How unstable is it along the warm front? Is there a northern stream jet that can help focus the warm frontal circulation? Those are things that vary from storm to storm and things you need to look at as you do this. But overall, what's going to happen is generally, in most cases, the cold frontal side will become the dominant band. It's how long that takes depends on the dynamics of every individual system. If you have more confluent flow, more of a jet on the backside of the trough that's digging in that case, again, you'll see the warm front, the precipitation form, but that's going to become more organized over time, especially if you can get a jet streak to start forming to the northeast of the warm front. And in that case, you'll see the jet streak or the warm frontal band extend southwestward over time and extend back to the north side of the trough that's forming behind to the northwest of the cyclone system. There may be a convective line that forms along the cold front, but it's going to be rather detached from our warm frontal precipitation, and it doesn't move northward like we saw in the other case because our jet streak is still diving southward, and our dry slot's not moving north, so you can't bring that unstable air along the cold front northward into the trough. So in that case, the frontal circulation within the trough stays focused on the warm frontal side. So thinking of that, let's go back to our March 23rd, 2016 case. And let's thinking about especially our first case, let's look at how the radar evolves and then apply our conceptual model to it. Because when you think about this, think about what if I had a mesoanalyst who was looking for this stuff, who we knew this was going to happen. So if they were looking for the formation and convection, or where's the dry slot moving on GO 16 data? Do I see convection starting to form? Those type of things in the case like the November 2005 case, those can be real hints on how things are going to evolve and when they're going to evolve. So when I look at this, kind of think of it in that way and how you can message that information then. So we can see kind of a disorganized band of snow here at 10Z on the 23rd, across south central, based from southwest South Dakota through south central South Dakota into west central Minnesota. As we move ahead in time, you see this band begin to organize itself into a pretty narrow but pretty intense band. And as we head towards 15Z here, notice how we have a really nice band, albeit narrow band of snow, all the way from near the Nebraska Panhandle to north of Sioux Falls and then back towards La Crosse at this time. Probably only 20, maybe 30 miles wide, but some of the snowfall rates, especially here, we're on the order of almost 1 inch per hour. And that, we saw the pockets of 6 to 8 inches of snow that occurred. So as this band continues to organize, we see it especially in Minnesota, it becomes a little bit better organized in time. So we head towards 18Z here. And now we're beginning to see maybe some striations in the radar across northeastern Nebraska. But these are moving northward, and they still kind of have the view of these very narrow bands of snow or precipitation, probably within a pretty unstable area. It's not convective looking in the sense, as we'll see in a little bit, but there probably is evidence that there's stronger lift beginning to move northward. And so some of the instability in that center of that trawl that we see is beginning to release, and you're seeing kind of striations of snow above the warm frontal surface. And as they move northward, you're going to see that those bands begin to merge with our primary band across South Dakota and Minnesota. And as it does, you see by 21Z, this looks like a really intense band of snow, all the way from probably Green Bay area through Minneapolis to near Sioux Falls, and then down through just north of North Platte and into the Boulder, into northeastern Colorado. So a really nice band of snow has developed. In fact, at this point, you think that this band is probably the best it has looked in its time. But look to the south, and you can see, if I go backwards, this convection beginning to develop across southeast Nebraska. If we had a satellite picture, which unfortunately I don't have, what you would see is the dry slot has begun moving into northern Kansas. And we've gotten convection that's now starting to form along our mid-level theta E boundary across southeastern Nebraska. This is the cold front that's beginning to come in. And so even though this band looks really strong, this development of this convection is probably a harbinger that this band's lifespan is coming to an end, at least over portions of Nebraska and South Dakota, and eventually over Minnesota and Wisconsin as well. So as we continue to move forward, see this convection continue to form. Actually, I think some of it was even severe in Iowa and Missouri. Again, the band still looks very good at 18Z. We were having about 1 inch per hour snow here in Sioux Falls at this point. Looks really good here in Nebraska, but we continue to move forward, 22, 23. Watch the band in Nebraska and South Dakota. By 0Z, the northern band has really decreased. Again, go back to 22Z, then 0Z. Look at how much it's weakened, and look at how our new band has begun to form across Nebraska. This is the second band of snow that produces the 8 to 14 or 16 inches of snow in that second band. And in a matter of only 2 hours, the northern band has really weakened and is about to dissipate completely from southwestern Minnesota into Nebraska. And the southern band has become the dominant band. As we continue to move forward, our convection moves eastward, and our band continues to form across northern Iowa, and the northern band continues to weaken across Minnesota. Hit 230Z. By now, the dominant band across Minnesota, Iowa, and South Dakota is along our cold front. The northern band has completely disappeared at this point. And as we head to 6Z, you can see the band still remains across from central Nebraska all the way through northern Iowa. And it's kind of beginning to merge. The two bands are merging across Wisconsin as we look here. And if we continued, you'd see that process occur. So when we go back to our snowfall map from the very beginning, I would argue that having two bands is predictable. Is it predictable where those bands will be? Probably not real predictable. That's a very much more unpredictable aspect. But the idea that there would be two bands would occur is something that is predictable, even 24 or 36 hours ahead of time. So then your job becomes, how do you message that? How do you tell people there could be two areas of heavy snow and an area where they may not see snow? because you probably still have to put out a warning in this area because it's probably not going to be certain. There's probably going to be a lot of uncertainty exactly where each of these two bands are going to set up. How far north will that cold frontal band go? I can tell you that in the models runs 24 hours earlier, this cold frontal band actually ended up over Sioux Falls, not over Sioux City. So you probably have a warning in this area. So somehow you have to be able to tell your partners that, well, we have a warning, you know, in this area here, Minneapolis and Sioux Falls does. There's probably going to be a place where you may only see 2 or 3 inches of snow, whereas to the north of there, you could see 4 to 8, and to the south of that area, you'll see another area of 8 to 16. And so you kind of plant the seed early, but then you have your mesoanalyst who's looking at the radar data, telling you when that process is occurring, so you can nail down that information and then pass that information on to partners, onto the media as quickly as possible. So that's everything. Are there any questions?